Welcome to Part 11 of the CipherVibe Cloud Security Capabilities series. This episode explains Container and Kubernetes Security, why it matters, how the capability works, which mistakes weaken it, and how to build it in a measurable way. Container and Kubernetes Security covers the software supply chain, orchestration control plane, workload configuration, network boundaries, secrets, and runtime. The goal is to prevent vulnerable or overprivileged workloads from becoming a path to cluster, cloud, or data compromise. The key idea is that a security capability is more than a product feature or a collection of alerts. It combines people, process, technology, decision rights, evidence, and continuous improvement. We will examine its architecture, operating workflow, failure modes, defensive controls, implementation roadmap, and useful metrics. Coverage is not the same as effectiveness. A dashboard can show thousands of checks while the capability still fails because evidence is stale, ownership is missing, or remediation is never verified. The business outcome should be explicit. Teams need to know which loss scenarios the capability reduces, which systems are in scope, and which remaining risks require a conscious decision. To understand Container and Kubernetes security, start with its architecture and vocabulary. The capability should create a traceable chain from source evidence to a security decision and then to an accountable action. First, image security examines packages, malware, secrets, configuration, provenance, signatures, base images, and deployment reachability. Second, Kubernetes authorization combines users, service accounts, roles, bindings, admission policy, and cloud identity integration. Third, workload security includes security contexts, capabilities, host access, volumes, network policy, resource limits, and secret delivery. Fourth, runtime protection observes process, file, network, system call, orchestration, and cloud behavior after deployment. These concepts need shared identity, timestamps, provenance, ownership, and access control. Every summarized risk should link back to its source evidence and disclose missing information. A sound architecture separates collection, normalization, analysis, policy, workflow, and presentation. Teams can then test freshness, identity resolution, policy results, owner routing, and closure independently. Design for degraded conditions. Providers impose rate limits, schemas change, credentials expire, and events arrive late. A professional capability reports uncertainty and health instead of presenting incomplete information as fact. Trust boundaries deserve equal attention. Identify where data crosses accounts, tenants, regions, vendors, privilege levels, and administrative domains, then apply authentication, authorization, validation, encryption, and audit controls at those boundaries. A useful operating model for Container and Kubernetes security follows a repeatable evidence lifecycle. First, inventory clusters, nodes, namespaces, controllers, workloads, images, registries, service accounts, and external exposure. Second, secure build pipelines, use minimal trusted base images, generate provenance, sign artifacts, and verify at admission. Third, apply workload standards for non-root execution, read-only file systems, dropped capabilities, resource limits, and restricted host access. Fourth, enforce namespace, network identity, and secret boundaries according to application trust relationships. Fifth, monitor runtime behavior and investigate drift between declared configuration, deployed workload, and active process behavior. The workflow does not end when a ticket closes or an API returns success. Security closure requires fresh evidence showing that the risky condition is gone and does not immediately recur. Ownership should be established before urgent findings arrive using service catalogs, business applications, on-call schedules, and escalation paths. Prioritization should explain the influence of exploitation, reachability, privilege, data, business criticality, compensating controls, and confidence. Repeated findings should drive changes to secure templates, defaults, libraries, identity patterns, and architecture standards. Define escalation points for missing owners, disputed priority, failed changes, and evidence that suggests active compromise. Those conditions should move into incident or risk governance rather than remaining indefinitely in a routine queue. The fastest way to evaluate container and Kubernetes security is to study how the capability can fail. First, fixing an image tag without controlling mutable tags allows vulnerable content to return. Second, cluster admin bindings and powerful service account tokens create rapid privilege escalation paths. Third, host path volumes, privileged containers, host networking, and unsafe capabilities weaken isolation. Fourth, admission policies that fail open or exclude important namespaces create preventable gaps. Fifth, ephemeral workloads disappear quickly, taking local evidence with them unless telemetry is exported. These failures share a pattern. A local measure looks successful while the full outcome is weak. A connector, scanner, or repair can report success while coverage, exploitability, or recurrence remains unresolved. Measure whether the program improves important coverage, shortens exposure time, removes attack paths, and prevents recurrence, not how many alerts it produces. Exceptions need a reason, owner, compensating controls, approval, and expiry. Automation should reflect confidence, reversibility, blast radius, and business impact. Test both through controlled failure exercises. Correlate weaknesses instead of reviewing them separately. A moderate configuration issue, broad identity grant, exposed service, and sensitive data store may combine into a severe path even when no individual alert looks critical. A dependable container and Kubernetes security program uses defense in depth. No single scanner, policy, gateway, or agent should be expected to carry the entire outcome. First, use trusted registries, immutable digests, image signing, provenance verification, and admission enforcement. Second, apply least privilege to users and service accounts, disable unnecessary token mounting, and rotate credentials. Third, enforce pod security standards, network policies, secret managers, resource limits, and protected control plane access. Fourth, continuously assess cluster configuration, workload posture, image risk, exposure, and attack paths. Fifth, export audit and runtime telemetry, test containment, and preserve evidence outside the affected cluster. Control design should include preventive, detective, responsive, and recovery layers. Together, they establish safe defaults, identify drift, govern containment, and restore service. Least privilege applies to connectors, agents, orchestration identities, data stores, and administrators. Scope, separate, monitor, rotate, and test their access. Every control needs an owner and test strategy. Validate it with representative assets, negative cases, simulated attacks, provider failures, and rollback exercises. Integrate controls with engineering through clear pull requests, owner routing, reusable fixes, documented standards, and fast feedback. Preserve an evidence trail from detection through decision, approval, change, and verification. That lineage supports investigations, audits, lessons learned, and fair performance measurement without forcing teams to reconstruct history from separate systems. A practical implementation roadmap for container and Kubernetes security should build trust before scale. First, inventory production clusters and define an approved workload baseline. Second, secure image sources and block the highest risk workload configurations at admission. Third, reduce cluster and service account privilege, then implement network segmentation. Fourth, add runtime detection and incident exercises for compromised workloads and control plane credentials. Fifth, measure systemic improvements in templates and platform defaults rather than fixing individual pods repeatedly. The roadmap is incremental because a focused production scope lets teams validate evidence, ownership, workflow, and control safety before scaling. Useful measures include signed image deployment rate, privileged workload count, cluster admin principal count, admission violation rate, and runtime sensor coverage. Give every metric a precise definition, data source, owner, and known limitation. Pair lagging indicators such as exposure age with leading indicators such as coverage, control health, exception expiry, and secure template adoption. Maturity means the organization can discover important risk, explain it, assign it, act safely, verify the result, and learn from recurrence. Review the roadmap quarterly. Changes in architecture, threat activity, regulation, business strategy, and provider services can alter both priorities and assumptions. Retire metrics and controls that no longer guide useful decisions. For more cybersecurity market intelligence, research, and educational briefings, visit CipherVibe.com. CipherVibe is operated by Cloudsectech LLC. This video is general education, not legal, compliance, financial, or incident response advice. Never access or test systems without explicit written authorization.